Hello everyone. Thank you all for showing up for what we believe will be a very exciting and informative webinar, and kicking off with the fall bit of our webinar series for the Data Science Education Community of Practice program. So today we're going to provide some information and discussion about data science career paths and industry for physicists. And to help us with that, we have an all-star cast of panelists. And so one of our panelists is a longtime contributor to the APS topical group on data science, Nima. So Nima is a research staff member at IBM Research in Cambridge, Massachusetts, where he works on AI for science and also with graph neural networks. He received his PhD at Boston University in 2016, working on complex systems. He was formerly a research faculty at Northwestern Institute for Complex Systems and a postdoctoral fellow at the Network Sciences Institute at Northeastern University. Also joining us today is the esteemed Dr. Jennifer Hobbs, where she's the director of machine learning at Intelinair, an ag tech startup where she leads an international team of researchers and engineers in developing machine learning models to provide insights to farmers. I could go on more about her qualifications, but I'm sure that she'll tell us more about them. We also have James Antonelli, who's a senior manager of data science at Blue Cross Blue Shield of Illinois, where he leads a cross-functional team responsible for a growing suite of predictive models focused on patient outcomes, etc. We also have with us today Tony Chu, who will be serving as artificial intelligence technical advisor at Johns Hopkins University Applied Physics Lab, so not so far from me. And he's led a variety of data science efforts in both the government and commercial sectors. So I won't go into their backgrounds because they're going to tell us a bit about their path into data science from physics and where they actually use physics in their careers today. Just to sort of manage the sanity, there should be a note that some of you may not have seen it with Zoom, is that if you have questions, please use our Slido link instead of the chat or the Q&A feature. This will help us surface them and allow you to vote on which questions you find interesting. Also, we'll post some notes for joining our community, both our Slack and our newsletter, where you can be informed about events like these and our own activities to develop modules for data science education in the physics context. And so with that, why don't we get started? And let's start with Jennifer. So enlighten us.
Already, are we able to see the slides? Everything looks good?
Mm-hmm.
All right, terrific. Well, I'm excited to be here. I'll talk to you a little bit about how I kind of got to where I am. As you heard, I'm the director of machine learning at Intelinair, which is an ag tech startup, and I'll spend a little bit of time at the end walking through that. As far as my background, I was at Northwestern for a long time, so undergrad through PhD. I started in a special program called the Integrated Science Program, which let me take a lot of upper level courses across a variety of sciences. Essentially allowed me to not make up my mind exactly what I wanted to do at the time, because I knew I loved science, particularly had an interest in physics. But more than that, you're an undergrad, you don't necessarily know. But I did love physics, so I also majored in physics and math. Stayed at Northwestern to do my PhD, working with some advisor. I'll go into some of that. And then actually during my PhD switched my focus more into computational neuroscience, although I remained in the physics department. So I'll go through a little bit of that, but I think one of my takeaways is that I think people like to think of career as a very straight linear approach, how we got to where we are. But there's a lot of, let's say, meandering, but all sort of around a central interest in the courses I took, the research I did, the positions that I eventually held in industry. So starting out,
Jennifer, you're in the presenter mode.
So what, you don't see this slide right now?
We see the slide. It's just that we also sort of see, you know, like sort of the things about title and appearance, etc. So
let me try.
If you press play, it will probably go away.
Yeah, this is what I tried before. Now you said you see the other.
Yeah, this is perfect now.
Now we see it. Yeah.
Now you see it. Okay, very good. Great. So yeah, right. In I think my sophomore year, I started working with Heidi Shellman at Northwestern. Now she's at Oregon State doing work on the Minerva experiment at Fermilab. So when I was on this we were still in the construction phase. So I did a lot of work developing a clear fiber QC DAC, some of the early hand scanning work. And then as part of my senior thesis was doing sort of a side project on this glass speed calorimeter that we were attempting to develop. But I really loved being there. I loved being out at Fermilab. I liked the work that I was doing, and liked it so much that I continued to stay there into my PhD. But about the second year of my PhD, I realized that as much as I love the detector construction and everything like that, that's not really where my primary calling was. And so I decided to switch into a computational neuroscience lab. So I stayed in the physics department, but continued to do research with a professor in biomedical engineering and mechanical engineering. So here we were studying how the brain encodes touch through behavior, as well as some neural recordings. And that's got me sort of vaguely involved in, we'll call it machine learning, but it was basically glorified logistic regression at the time, and a little bit of very crude brute force computer vision that I taught myself. But the work that I did led to a top paper prize from the Journal of Experimental Biology. And for as much as I was doing with, let's say, around the neuroscience, the brain, what really sort of interested me, I think deep down, was some of the computer vision. So here we have one of our, high-speed videos of this rat exploring this laser light sheet so that we can track contact patterns and understand how they're being represented in the brain. So this is sort of where maybe the seeds of interest in computer vision were planted. But also while I was in graduate school, I was doing a lot of work outside of the lab. I was very involved in the residential college system, working with undergraduates, doing lots of teaching. I think I did every teaching program that the university offered for graduate students. I was involved on a committee with the provost committee around educational technology. So really involved in a lot of the other elements of university life beyond just research. And I'd always thought that I would stay in academia, but then about 18 months before I was ready to graduate, realized that this was maybe not the right path. I had concerns around, job placement and how long would I spend doing a postdoc. And I knew my interest was sort of, again, more in the computer science, computer vision area, and that I would have a hard time maybe getting a postdoc there. And so I'd have to sort of spend time developing new credentials to actually move into the area that I wanted. And, at some point decided, to sort of take the leap and move into industry. So when I was leaving, as I was finishing, we had not hit this data science boom yet. You might have heard words around big data or analytics, but we certainly were not in sort of the era that we are now. And to that end, there also was not sort of this understanding of how, people with PhDs, particularly in physics, were sort of moving into the industry space. When I, went and met with the University Career Center, there was a lot of confusion over, what do you want to do? It's like, well, I don't know. What does one do with the PhD in physics if they're not in academia anymore? So I think I applied to something like over 200 jobs, from everything from management consulting, software engineering, financial, high frequency trading. I'd known that a lot of physicists had gone that route. I applied tons of places, heard back from 3, got an offer at 1. And a lot of things that I was hearing at the time where people are sort of confused as to what to do with somebody with a PhD in physics. A lot of that has gone away. I think this big, again, interest in machine learning and data science has changed that. But for me, that was a lot of what I had to do was sort of explain how, sort of specific area of research that I had done, would broadly translate into helping them achieve their business goals. So where I ended up first was Zurich, North America, based in Schaumburg, and as a risk insights analyst. So this was a new group that they were creating, sort of a fusion of an old analytics actuarial department and this new data science department coming together. So I built predictive models, prospecting, resource allocation, a variety of projects within that organization. Ironically, I applied for a data science role there, but when I did the interview, the person doing the hiring, the head of the department, was sort of more impressed with my ability to do problem formulation and to take the business need and map that to a technical project that would need to be solved. That he said, well, would you consider this other position, this analyst position, which is more on that, sort of early stage, almost had a certain project management sort of feel to it. Then I said, sure. And as it turns out, a lot of the work that I did was sort of very hybrid. So, but it was great. I loved being there. There was a lot of, I learned a ton, both about the insurance space, as well as, seeing sort of the growth and, of this new organization. But after I'd been there not too long, an opening occurred at a company called Staff to Perform, which is a sports data and technology company in Chicago. And I'd always sort of tracked them, because even going back to the time I was a child, I always wondered, I said, like, why don't people study sports in terms of understanding motion or how, action detection? Why don't you build, why doesn't somebody study the math of sports? It's sort of more constrained. It's not, it's more interesting than some motion, but it's not, just fully random, in today's day and age, autonomous vehicles. It's got this nice sort of hybrid middle ground. It seems very interesting to me, but I had never seen any roles come available. Most people, when I would say that, told me I was crazy. But I always had this idea, and I sort of, kept my eye on this company again from the time maybe I was in high school. And then all of a sudden this role for a data scientist occurred. And as it turns out, it was the first time they had created this division within the company. So I was the first external hire. There were several people that had come in through some mergers, but again, had the opportunity to see how this this company formed. And there I did a lot of work on the data engineering side, being one of the first people there. There was a lot of modernization efforts around how do we handle and think about huge amounts of data? How do we organize the data so that we can even enable machine learning and AI to occur? And then as I was there a number of years and moving into a managerial role, we did have some opportunity to do some research, published a few papers both in the computer vision as well as more the broader sports analytics space. But my work was focused there primarily on some of the spatial temporal multi-agent tracking and analysis, understanding how players move and create formations and things like that. Again, as well as doing a lot of more on the product management side. So I was there for several years. And then for the past almost 3 years now, I've been at Intelinair, which is, again, an ag tech startup. We're based out of Indianapolis. I'm remote in Chicago, and the bulk of my team is actually in Armenia. I got back from visiting them just middle of last month. So right now I manage a team of about 20 across the US and Armenia. And this team is responsible for building all the computer vision and machine learning models to detect patterns and characteristics of interest from the imagery that we collect. We collect primarily high resolution imagery from airplane, but also high res satellite. So in this 10 centimeter to 50 centimeter per pixel range, most people probably don't have a feel for what that looks like. I'll show you a picture in a second, but like if you've seen public satellite, like in your iPhone and that's usually 3 to 10 meters, sometimes as low as 30 meters per pixel. Or maybe you've seen drone photos that are, sub-centimeter, where you can actually see the ladybug on the leaf. We're in a sort of an intermediate ground where you can see huge amounts of the field and cover territories at scale, but still enough to see individual, crop development. So it has a lot of interesting challenges, and we have a ton of data that comes in. So my team is responsible for sort of the end-to-end from the problem formulation, how do we solve the user's goal based on the data we have available, the techniques available to us, as well as the model development, deployment, monitoring, and all of that sort of goes into creating and taking care of a model that's living in the real world and has real customers. I'm still very engaged with the academic and tech communities. We organized a workshop at CVPR called Agriculture Vision for the past 3 years. And then another part of my job is around grant reports, collaborations with other researchers, and giving talks and seminars. So we collect a lot of data, imagery, a bunch of different other sources, weather, soil, planter data. All of this GIS data allows us to create this rich description of the field. And here's sort of an idea of what some of this imagery looks like. So we have like a zoomed out picture of the field, but because of the resolution we collect it at, you can see the individual rows where there are gaps occurring. And then this picture on the right is NDVI. So it's a vegetative index because we're collecting multispectral imaging, so including like the near infrared, and allows us to track things like biomass and vigor and see, where is the crop doing well as opposed to where it may not have emerged. From this, we can generate different alerts around weeds, replant opportunities, or do plant counting. So here was a work we did off of an NSF grant to detect flowering pineapples in Hawaii. The cool thing here, right, we used a density estimation approach similar to what you might use in dense crowd counting, so that we could, in flat computational time, be able to count, a couple million pineapples across this whole field without, taking forever for the compute to run. We generate our alerts geospatially, know how different fields are doing relative to one another, if there are weed outbreaks or emergence issues. So there's sort of some of the things that we do there. And then outside my sort of main work, I still try to stay very involved and connected to the academic and physics communities. I like to give a lot of talks like these at the university, usually around women in tech or in this sort of career paths for physicists domains. Recently, I've been excited to start serving as a member at large with GDS. And then during the pandemic, a colleague and I started this lapsed physicists wine and cheese social that we've been hosting at some of the conferences, just noticing that as we get more and more physicists in the machine learning space, just trying to keep them connected, having conversations, sharing ideas and things like that. And then I also stay connected through reviewing for a number of the top ML conferences. That's my rundown. Thank you.
All right, thank you very much for that, Jennifer. Virtual round of applause. I guess I can actually give some applause. Again, please place your questions in the Slido for Jennifer, but we'll now move on to Nima.
Okay, hello everyone. Thank you, Jennifer, for the very nice, walk through your career. I do not have many slides, but I figured it would be actually useful to maybe share part of my work, and maybe just a little bit, some pictures would help as I'm talking along. So I'm just gonna share my screen for a second, and
Nima, I think you muted yourself.
And you'll also probably want to again, go to presenter view.
I think there was a problem with the sharing, so I'm gonna just try to share again, but this time maybe I'll go here. Can you hear me now?
Perfect.
Okay, good. So I also started my career in physics. Right now, I'm a research staff member at IBM. I just started like 6 months ago. And prior to that, I was, as William mentioned before, I was a research professor at Northwestern. So my career was kind of odd. So I was very interested in theoretical physics, and at the same time, I also really liked doing hands-on things, building small robots, or programming. I did not have a huge background in programming during my most of my physics years. I did actually start off in my bachelor's. I first started off as a mechanical engineer, and just to give you a perspective on this, so I'm from Iran. And in Iran, you actually take this nationwide entrance exam to enter the public universities, and there you have to choose what your top places are that you want to go, as well as the field you want to study. So you have to know from the beginning what you want to study. And I wanted to go into physics, but the whole environment in Iran was saying, there's no jobs for physicists, engineers are in demand because it's a developing country. So by some encouragement from other people, I ended up choosing some engineering fields ahead of the physics field that I wanted to enter. And I ended up starting in that engineering, in the mechanical engineering field. I didn't really like it at first, the first year, but I did enter some robotics teams and started learning some MATLAB, and it was fun. But through some legal ways that you could change your field back in Iran, which was actually kind of difficult. It might be surprising for people who are here in the US who might not even choose their major up until late in their during their bachelor's. So eventually I managed to change into physics, and I really loved it. And so I got my bachelor's and master's, and then I came to the US to study physics. I struggled actually quite a bit in my grad school because I was not able to find an advisor that could really work with me. So I feel there were quite a few of us in our year who had to shop around quite a bit. We worked a little bit with some advisors, and they did not have the money to pay us. This was right after the the recession in 2008. So I actually was teaching until my fourth year as a TA almost every semester, and at the same time trying to do research, which was very difficult. And I did switch many fields when I worked on many different branches of physics during my grad school years. I started in condensed matter. Then I did a little bit of particle physics. Then I finally published a paper in quantum fields in curved space, basically black hole mechanics. And then basically the department told me you have to find an advisor that can pay you. And I had interest in data science related work. I had actually, during my first summer, worked briefly with Professor Gene Stanley, who worked in complex systems. And then I had switched to particle physics. So then I went and talked to him again, and he kindly accepted me into the group. And that was really when I started switching to more data science related work. So this was the 5th year of my PhD. And then, so within 2 years, I graduated. And that was when I first learned Python. Prior to that, I was using Mathematica, maybe for the general relativity computations that I was doing. But I slowly started appreciating this power that being able to code and really materialize what you need to do. I started appreciating that more and more. And then during my postdoc, I started off working in the on network science with Professor Barabasi here at Northeastern. And during that time, I realized that the train was going toward machine learning. And what I mean by that is I figured a lot of the things that we were doing, data science related stuff in complex systems, was a lot of handcrafted models that didn't have a lot of flexibility. Basically, you had to, when you were talking about a social network and how a certain effect was emerging, whether you give a weight to your first neighbor or your second neighbor, that was predetermined in the physics-like models that we were using for describing these complex systems. But at the same time, I learned about these machine learning models, and I realized that they were a lot more flexible. Basically, you didn't have to have a fixed model for how the system is behaving when you started modeling the system. Rather, you could build these very flexible models for doing this. So that was my entry point into machine learning. Basically, by the end of my postdoc, I had published a paper in NeurIPS on graph neural networks, trying to understand them better, really. And then I moved on to Northwestern, started as a research faculty in a computational social science lab, where a lot of the work that we do is related to basically applying, trying to model social behavior. I'm just going to quickly share just a slide with you. Sorry, let me just, I'm just going to quickly just open another slide. I should have, made separate slides for these, but I just want to show you a screenshot from one of the papers that we published there. So this is from a tutorial that I have given a few times about machine learning and its uses in science and social science. So my focus right now is a lot about machine learning for science. So back in Northwestern, we published this paper. So I was lucky to be part of this paper where we analyzed how the careers of creative people, so scientists and artists and directors, were evolving over time. And one interesting thing that we did there was we used a lot of machine learning to convert these seemingly qualitative data that you have. Let's say you have a painting, or you have a writing, or a screenplay, or paper. We use machine learning to convert these into processable data, like into vector representations. And from that, we were able to basically, let me show you something more from this paper. So these are just ways that we use to convert this data into vectors. I'm not going to go into that detail, but that allowed us to analyze the career trajectories of these creative people. And I felt this was a very powerful thing, that we could do this analysis of how humans are making decisions and how these things are evolving over time. And just lastly, I want to also mention to you a little bit more that the real physics of what we're doing, because a lot of people might go into data science and you might think that you may not be using physics anymore. But one of our last papers from last year was about designing a new machine learning algorithm, basically an architecture for a neural network that is capable of recovering symmetries or discovering symmetries in the data. And I actually use quite a bit of the tools that I learned in physics in this paper, which was basically using Lie groups, Lie algebras, and so eventually we ended up designing this architecture, which was able to encode Lie algebras into the neural network architecture. But the interesting thing, the twist at the end, was that the final thing I discovered when I was working on that paper was you can actually, let me just bring up that slide. You can actually recover free field theory. You know, if you're familiar with field theory in physics, you can recover the action of the free field theory from this architecture if you design this most simplistic model using this neural network layer. Basically, take a single layer, take some input phi, and then it applies the Lie algebra transformations, and then you're minimizing some square error. That loss function is equal to the action for a field, basically a free field theory in physics. So we are trying to explore this further to basically, hopefully, try to use models such as these that can encode symmetries to actually build more flexible physics models. So instead of you ahead of time putting in all those polynomial terms that you expect to be inside your field theory Lagrangian, you can actually kind of train a black box, which is can be a very flexible function of your fields, but at the same time, it's guaranteed to at least preserve the symmetries that you expect the system to have or you want to discover in the system. So right now at IBM Research, a lot of the work that I do is still basically theoretical machine learning. One of the papers we're working on right now, submitting hopefully in a couple of weeks to ICLR, is about symmetries in the parameter space and the loss landscape of neural networks. And we're finding these interesting patterns of, again, Lie groups acting on your parameters. Basically, think of it this way, that we usually think of machine learning loss landscapes as this very glassy system with like a lot of minima that you can probably not, it's so complex that you cannot understand. But it turns out there is a lot of structure in there. And basically the architecture of your neural net, how you are putting the layers together, determines a lot of structure inside this loss landscape. In particular, it results in a lot of valleys inside this loss landscape. So something very interesting that comes out of this is you will have symmetry transformations that move you along the valleys. You also have a full Noether's theorem. Basically, you can associate these continuous symmetries with conserved quantities that are basically while you are doing your training and doing gradient descent, these quantities do not change. So they are, if you think of gradient descent, the training process as a dynamical process, these variables are not changing. So really all of those concepts, and I had to teach my CS background intern this summer. Actually, she also had a physics background in the undergraduate, which was very helpful. And she was very diligent. But we went through the whole theoretical foundation of classical dynamics in this project. And I taught her everything again about like Lagrangians and Hamiltonians and Noether's theorem and everything in order to do this. So it was quite interesting that the amount of physics that I require in my work, or at least that I can use in my work, is quite a bit more than maybe someone from the outside thinking a physicist went into machine learning might expect. So I do think a lot of these, at least the theoretical tools, as well as the way of thinking that physics taught me, is helping me a lot in my work. And it's really a big part of my work right now.
Thanks,
and
Nima.
With that, yep.
Awesome. So just remember to put your questions in the Slido. I noticed that some are already coming in. And next up, why don't we have Tony? Can you take maybe, like 10 minutes or so and tell us a little bit about your path and your insights?
Yeah, sure. Happy to. Thank you again for having me. Thank you to Jennifer and Nima as well for their excellent presentations. Thought that was very interesting, their work. And I think for my slides, I'm going to keep it a bit high level, talking first on this slide about my academic career path, and then on the next slide, some thoughts about what I think is useful from my education as well as from my industry experience. And let me get this slideshow view going. Okay, and I hope everyone can see these slides. Right, good. So great, thank you. So I did my undergrad in physics a while ago, and to give similar context, I did not know anything about the term data science or the field of study of data science or data science as a career when I was an undergrad, and even through my graduate studies and my time as a postdoc. What I pursued was not specifically geared towards a data science career, but I think for me, what I found very valuable from a physics education perspective is that solid foundation in things like statistics, linear algebra, calculus, and quantitative reasoning, where you're given a problem and you need to kind of dissect different components and translate that into a mathematical problem that you have the tools to solve. And I think that kind of transferable skill with that mathematical foundation has really served me well going forward when I transitioned into data science. I think as an undergrad, I could have taken more courses that involved programming, but that again wasn't really my kind of mindset when I was doing an undergrad. But I was fortunate enough to be a part of our undergraduate research program at Cornell, where I got to design some different research projects on the side during the school year and during some of the summers. And that's when I kind of got more hands-on experience with computational work for some of those projects. And I really liked, so as part of that undergraduate research program, I did work in the lab and I did computational work, and that's kind of how I quickly learned that I don't enjoy working in the lab as much, and I like to use computers to solve things and do like the more theoretical stuff. And I also fell in love with general relativity. I just thought it was really elegant. I took some courses as an undergrad, and like who knew tensors would kind of be useful later on outside of that. But so some of those concepts as well as computational work led me to the field of numerical relativity during my graduate school and postdoc. So without knowing anything about data science, I think I was very lucky to choose a field where you get to do mathematical theoretical stuff, but also it heavily integrates computational work. The problems were not necessarily like machine learning related to machine learning, nor did I really have a clue of machine learning at the time, but it did introduce me to a lot of important concepts that I think are still useful even as a data science. Besides just kind of how equations are translated into computational operations, numerical algorithms to solve those types of things. Also, the concepts of high performance computing, which I think is kind of increasingly more important as we think about scaling and deploying machine learning models in the industry. So I thought that was really helpful, and the environment, of course, that you get being in grad school and a postdoc surrounded by really smart people. I think that's where I met Anil when I was in grad student at Caltech, and he was a postdoc there. I think that community really is a great boon to learning things as well. And it wasn't until 2015 that I just thought of doing stuff outside of academia. And at that time, that was still not data science. I applied for this position. Title was research analyst at the Center for Naval Analyses. That's a federally funded research and development center located in the Washington, D.C. area where I am now. And that job involved a mix of operations research, simulation, data analysis. And it was a little bit later, a few years into that job, that data science kind of emerged as an area of interest at the workplace for me. But I think just transitioning to that job itself, it was really transferable skills that they were looking for. In fact, in my interview, I gave a seminar about my research on black holes, which is not really a practical thing for them, but it still illustrated how you can translate like a real problem into mathematical form, and also how to practically solve it with computers. So, and what the significance of those results are, how are they meaningful, and so on. But it was kind of in the later part of my time at Center for Naval Analyses where data science started to pick up. I got involved in some of that work, and I was really interested in doing machine learning. So, I think when some companies talk about data science, it kind of, sometimes it can mean a broad range of things, whether it's more on the statistical analysis side, more on the data engineering side, or the machine learning side. And I found that I was really interested in the machine learning side. And so I made some switches to gain more experience in that. And that led me to Accenture Federal Services, where I built machine learning models to predict recruiting, onboarding, and churn for an HR division in the Department of Justice. I also worked at Citibank, very different domain, where I used built machine learning models to improve data quality and detect anomalies in their enterprise data systems. And more recently at ECS Federal, where I was supporting a counterterrorism division in the Department of Justice, building some tools that use name entity recognition, information retrieval. So it's kind of a mix of different techniques, but the thing I really like about data science is just how widely applicable they are to different domains as well. So, I've jumped into different positions to gain different experience. And actually next week, I'll be starting, a new position at the Johns Hopkins Applied Physics Laboratory, which I look forward to very much. And the next slide, I'll just give some thoughts, my own personal thoughts about what I think has been important in my journey through academia and industry. So these are just purely my personal thoughts, not necessarily the best opinions, but I think if you're taking courses or one of the most important things you can get out of an undergraduate experience in physics is what I mentioned before, a solid foundation, some of the key skills like statistics, linear algebra, calculus and quantitative reasoning. And if possible, if you're interested in data science, try to find some opportunities to integrate coding. And that could be kind of instructor-led if they can design something through coursework, or if not, if that's not as available, try to find some outside projects as well. And I think when we're in academia, sometimes we just write like standalone scripts on our computer, things that are not as really maintained. But I think in industry, it's more and more important to be aware of software development practices, version control systems, concepts for DevOps and even MLOps. Not necessarily that you will be heavily doing that stuff if you're a data scientist versus like data and ML engineer, right? But just being more aware of that, I think, is more and more important these days, and it does help you stand out, right, from other applicants. And also, I think an important skill to gain is presenting the results and visualizing data, which may not be, which you may not have a ton of opportunity normally as a student, but if you can find opportunities for presenting at poster sessions or conferences, that's a great way to develop that skill. And I think, this is something that I kind of mentioned before, but if you're considering a job in data science, so I think it's important to know the type of data science that you're getting into. If you really want to be building and implementing neural networks, you don't want to be stuck using Power BI every day, right? So just be aware of what places mean when they talk about data science. And also be prepared for problems that are not neatly defined for you, right? And data, real world data, that's not tidy, and it's problematic, and being able to figure out issues with that and how to deal with that. And in terms of the environment, I think some key skills are stakeholder engagement and communication. You'll likely be working with people who don't exactly do the same thing as you, whose goals are not exactly the same as you. They should be broadly related, but sometimes they're not directly related, but you need their help to get stuff you want, or you need to understand their goals to better do your job. And they may not even be technical people. So being able to communicate across those channels, I think is important. And also be prepared to focus on practical results more than kind of making things as advanced as possible, which might be a difference between industry and academia, because usually the motivation for everything in industry is the business outcomes and the return on investment. And sometimes spending 3 months to get an improvement of 0.5% in accuracy is not worth it, right? So just be aware of that. And just from your own career perspective going in, which is something that I took time for me to learn, but is understand from your own career advancement perspective, what is important, what achievements are valued. So you're not, surprised, or, when it comes to evaluation time, where you stand, right? So that's, I think, just that's a kind of a general thing, but something to consider when you're going into industry. And of course, there are many many good resources out there, journal papers and industry blogs. I think it's also just helpful to browse job postings from time to time to get a sense of what companies are looking for in terms of the skills. So you keep your skills honed or just aware of the latest things that are in demand too. Yeah, that's what I have prepared. Thank you.
All right, thank you so much, Tony. Virtual applause as you can. So we'll move on to Jamie, but just before we do, a little bit of housekeeping is that we're coming up towards the top of the hour. We will get to the Q&A, and that will go on between 1 and 1:30. For those of you that do have to drop off, the Q&A and the whole session will be posted on YouTube, so stay tuned for those questions. But okay, Jamie, and if possible, if you can limit it to 10 minutes, that would be wonderful. All right, thank you.
Yeah, sure thing. I had some nice slides, but I have to allow my computer to show them, which means leaving the meeting and coming back. So instead, I'll just talk through them and just trust that I had a really awesome set of slides. Maybe you'll be able to share them afterwards, but I can just talk through the themes of it. So yeah, thank you so much, William and Anil, for the invitation. I'm really excited to be here. So what I thought I would do, I'll speak a bit to my career path, but mostly what I wanted to try to do was to pull some reflections together on what I found that I brought to data science by way of my physics background and some of my experiences working with other physicists who are now data scientists and working with people from other diverse backgrounds as data scientists. I've done a lot of technical mentoring over the years. So I wanted to pull out some themes with the goal of hopefully showing all of you that you really do bring very useful skills and mindsets that are fairly unique by way of your physics backgrounds into a field like data science. So yeah, I'm Jamie Antonelli. I'm a senior manager of data science at Blue Cross Blue Shield here in Chicago. My background, I did a PhD in particle physics, finished that in 2012, and then stayed on as a postdoc for 6 years or so before moving into data science. I worked on one of these experiments at the Large Hadron Collider, the CMS experiment, and I had a couple pictures to prove that I really was there, that it's legit. And I wanted to show those for street cred, but also because there's a group of about 8 of us in the picture. And just looking back at that, 2 of those people are still doing physics, are still in academic positions, but the other 6 have all moved into industry. One is an engineer at SpaceX, but the other 5 of us are all data scientists. So just to underscore the point that as with a physics background, you're very well positioned to move into data science. It's a very well trod path at this point. Okay, so I had 3 strengths that I feel like physicists bring into industry and specifically data science, and then also their kind of associated dark sides or what happens when those strengths go wrong. So the first one is confidence. And what do I mean by that? Physicists bring confidence in a few different ways. So confidence in science, this understanding that the world is knowable and that if there's something out there, a phenomenon, there is an explanation for it. You see this a lot in data. Something goes wrong with the data, and we're in this mindset like we can figure this out. So that's the second thing, is confidence in our own abilities to solve some of those mysteries, to analyze logically data and get to answers. And the third part of that is that we're not scared of math. Nima had some pretty fancy math on his slides. Honestly, I'm sure I saw that at some point, but it was. But I know that if I spent the time, I could dig in and eventually understand that stuff. And I think that's a confidence I don't see in a lot of people, data scientists without a physics or other hard sciences background, is they kind of throw up their hands when it gets too mathy. So that's great, confidence. But the dark side of this is hubris. So a kind of, irrational pride. Physics draws a lot of people who want to study really fundamental things, foundational stuff. And that's great, but that means we have a tendency to grow this habit of sort of thinking less of other disciplines, of the softer sciences, chemistry, biology, the social sciences, et cetera, humanities, which is really detrimental. And the way I see it a lot is a lack of appreciation for anything other than technical skills. So Tony mentioned this, that communication is paramount. You can build super awesome model, but if you can't convince people to use it without using any math, then it has no value. And so I think, physicists have a tendency to kind of look at this as a necessary evil, like, oh, I got to like talk to people. But it really is crucial to succeeding in industry in general. And then the third part of this is that it's easy to think that other job functions sort of exist just to support your work. So I work for Blue Cross Blue Shield. We pay insurance claims as a living, and our team builds models to make that more efficient. But that's not really, our team isn't the goal of the company. We are supporting them rather than the other way around. So that's a trap I've seen people sort of fall into. Okay, so moving on to the second strength is perseverance. So, along with confidence, we know that the answers are out there. We also understand that the answers may be hard to get to, and that they may be sort of murky even when we get to them. I mean, if anybody here really understands the double slit experiment, you're beyond me. The universe is complicated, and we're comfortable with that. So again, I see a lot of people look at the data, try something out, it doesn't make sense. They say, well, it doesn't make sense. So we have a propensity to want to dig in and go deeper. Also, we are comfortable with doing tedious tasks that still require a lot of attention to detail. So think of the pages and pages of algebra that we've all done in the course of our physics education, where one errant minus sign can screw the whole thing up. So you see that a lot in data work too. You really got to understand your data. And so it can be tedious to be doing the data preparation, but you really have to be careful about it. And I think that's something that physicists bring to the equation. And thirdly, a healthy skepticism of easy answers. I see this a lot of a sort of like this too much trust in algorithms. An answer comes out and they say, well, that's what the grid search told me is the best model to build, without thinking more reflectively about that. But I think we have we're oriented more towards wanting to understand why and wanting to doubt if something is too easy, seems too good to be true. The downside of this one is perfectionism. So I would say this is, going too much in depth on a certain subject. Oftentimes you'll be given a task and you need to be able to finish that task in a less than infinite amount of time. But there's always more work you could be doing, more understanding you could bring together. So it's hard for us to stop. So we often get this, we call analysis paralysis, where you're just slicing and dicing the data to death, and you've generated 15 different kind of competing narratives of what's going on, and it's hard to synthesize those back together and make any real decisions. So one of my coworkers likes to call this letting the perfect be the enemy of the good. Where in PhD programs where you have potentially years to mull over a given idea, in industry, it's more like weeks or months. And then so it's a mind shift there. And then thirdly, the last strength is curiosity. So I find this physicists, we have this desire to build an intuition around a given phenomenon or a given, in my case, like data set, where we really, some people preparing the data as a means to an end, but we really care about the data and we want to understand it. We want to know it. We want to garner insights from it. And I don't see that with a lot of people that don't have a hard science or physics background. And also another big piece is applying the scientific method. This is something that gets really ingrained in us, but I see a lack of for people with other backgrounds, where something comes out of a model, we see something weird in the data, and some people will throw up their hands and say, like, oh, this is weird, who knows why it's happening. But as physicists, I think we're trained to say, this is weird. Can I construct a narrative that would explain this, that's reasonable? Can I generate a hypothesis? And then can I go out and test that hypothesis? Can I design an experiment that would tell me whether this is right or not? And I find I'm often having to hold people by the hand through that sort of that mental process of where to go next when something unexpected happens. And then finally, the downside to this one is, I call it distractibility. So like perfectionism with too much depth, this is too much breadth. You know, it's we really enjoy knowledge, but if we're not careful, we have a tendency to just kind of accumulate as much knowledge as we can for its own sake. And this can lead us off the beaten path and down a lot of rabbit holes of things that we're following our interest. But it's surprisingly hard to keep an eye on the real value of a data science project when we're mostly focused and interested in the technical details. And so I think Tony was mentioning as well, like, there's this classic, like, oh, I could do this with a very simple machine learning model and do it in 2 weeks, but I could get a few % better performance with a neural net that'll only take me 6 months to train and understand. And we tend to get distracted by shiny things like fancy algorithms. And that can lead to just not providing a lot of value from a data science team, which is a downside to avoid. So those are the 3 strengths and weaknesses. And I had one final slide. Those are all very abstract, but I did want to give a shout out to some of the concrete tools that you might start working with to prepare yourselves for a career in data science. So Python data analysis packages. If I'm typing something, it's usually a pandas command for data manipulation, matplotlib for data visualization, or scikit-learn for modeling. Like if you know those libraries, you're in pretty good shape. SQL or SQL for querying data and slicing data. That's good to know the syntax of. In terms of machine learning, I'm humbled to be here with my fellow panelists because they're doing a lot of really cool machine learning stuff. We build a lot of binary classification algorithms. It's basically like, are you going to get diabetes next month or not? So we use a lot of tree-based models for binary classification. That's really 90% of what we do. So I would recommend, and I think a lot of the industry is that way. So if you're going to learn algorithms, that's a good place to start. And one last tool is, and Tony mentioned it as well, but version control. So we use Git and GitHub. And that it's nice to know the mechanics of how those tools work. But the main thing is, and Tony mentioned it, when you go to write code, writing with the understanding that other people are going to look at your code, they're going to use your code, and they might want to even extend and develop on top of your code. So coming to software development with that sort of mindset gives you very different priorities than thinking I'm going to write all this code to do a thing. I'm going to do it by myself, and then all I need to do is get the right answer, and no one else is going to see the code. And then one final note, I saw this in one of the questions too, but I plan to mention it, that I think one of the best things you can do is a side project, is some sort of, there's so much public data available out there. If you really want to be a data scientist, that should be really exciting to go get some public data and build something interesting. It doesn't have to be a fancy machine learning model. It could just be an analysis or a data visualization or something. But if I'm interviewing a data science candidate, I would love to have a conversation about something like that, as opposed to the physics research that you did, or brain teasers or these sort of things. I want to see that you're enthusiastic about data science to the point where you've put some skin in the game and spent some time working on a data science project on your own time. That's a really strong signal for me that someone will be successful as a data scientist. Great, so I'll end there. Thank you very much.
All right, so a virtual round of applause. And with that, we'll leap into the Q&A. And we had a nice segue from Jamie, which is, we'll extend to the other panelists, which is, what's the best way to be competitive in, data science? And I assume this is for getting a job. Is it to do Kaggle competitions and online certificates or personal projects? Or what are your thoughts, from the others, from Tony, Nima, and Jennifer?
I'd echo that, especially depending on where you are in your career. Having a project or something to show is really key. So especially if you're coming from a non-PhD, if you have your PhD, your thesis is somewhat, at least an element of long thought out, start to end work. You may need to do some mapping in that and sort of when you present that, emphasize things different, emphasize the problem solving as opposed to like some, wild piece of mathematical brilliance that you injected in this one step. But particularly, if you don't have a thesis project, there's tons of public data out there. Find something, go through, and really more than, I built this complicated model that does X, really seeing your thought process, articulate it. I think another thing that's really powerful is, like, again, the ability to deploy a model. You can get a T2 micro instance on AWS for free, like host something on that and just show that it works. That's super impressive if you're trying to go something more engineering focused. But having something tangible, in truth, no one's impressed that you trained X model and got Y accuracy. Like that, it's sort of the model's performance isn't a demonstration of your brilliance, and people know that. A lot of it, often it's the data that's the limitation. So seeing your thought process is really key.
Tony and Nima, would you agree, or additional thoughts?
Yeah, I think I agree a lot with what Jennifer is saying. And in a lot of interviews, they will ask you to talk about at least one recent project that you did and what were the challenges there and what were the difficulties. I would like to add that it also depends a little bit on the type of job that you apply for. So normally a lot of data science jobs, they would not be necessarily requiring writing new papers or that kind of research. But if you're looking for that type of research jobs, then they will it's going to be sometimes less of the brain teasers or the coding and more trying to understand your thought process to see like how smart you are about solving a challenge. So they usually give you an open-ended problem, and then you need to talk through your thought process as you're explaining it. In terms of how to get in, I agree with what Jennifer said. For me, I did not use like Kaggle or anything like that, and my job doesn't require me to necessarily do a lot of coding, but I do it as part of my job. But for me, it was always, I learned things through the projects that I was doing. Let's say for my research, I needed to use this machine learning model, so I went and learned it, or this framework, and I went and learned it. So it was more having to use it because of part of my projects, integrated into your work, I would say.
I agree with everything that has been said so far. I think in addition to all that, if to the extent possible, if you're able to demonstrate some understanding of the type of work that a company does, the type of problems that they're solving, and how your skills or something about your project can tie into that work. It doesn't necessarily have to be something that they will definitely use, but at least letting them know how you're thinking about it. So on top of showing how brilliant you are with your project, also it conveys to them why you might fit in, and just that you're considering that your place there seriously. And so I think that would help as well. Yeah, like the Kaggle, HackerRank, LeetCode, and that kind of stuff. Sometimes it's inevitable that you have to go through those things in the interview process. I don't think like I wouldn't necessarily say that it's a good thing, right? But it's just like something that sometimes is part of their standard thing you have to do. Yeah, I don't, yeah, it's, so it's just like a necessary evil sometimes, that you have to like just know how to do, if that's the type of job you want. Like it's, I think, more in the tech industry where you would have to go through that type of process, as opposed to like a research position. but it's just something to keep in mind.
Yeah, if I may, I wanted to just add one more point that one thing that we do not learn, and I still struggle with, are algorithms. And because a lot of people, so a lot of these jobs for data science are still dominated by computer science people and are in the tech industry, they all come from a background which learns the algorithms book, that massive book in their freshman year, or first couple of years in college. And they, unfortunately, I would say, kind of have a heavy emphasis on knowing all these algorithms, these known algorithms. So it has kind of become a gatekeeper for entering many of these tech industry jobs. So if I wanted to say something to invest in to at least make sure you can get a job, is go on Leet Code, like this website where people can solve simple algorithm coding problems, and try to go through as many of them as possible. And just make sure that you know the basic algorithms and graph traversals and binary search and so on.
Okay, so continuing, thanks for those answers. Looking back to your career, do you recommend a postdoc for people who are thinking of switching to industry eventually?
Maybe I can start there. Yes, if you don't have any other choices, but no, if you can get a job, because I feel it's going to be a waste of time, not only for you, but also for the team, because if you're not that dedicated to that research, and I totally understand that it would not, that because of the low pay and the uncertainty of the future and the short time that you have in postdoc, there is a lot of stress on postdocs. So I would say no, not if you have other options. If you need to buy time, then sure, but it's not a very wise thing to do.
And definitely depending on what you're trying to do. I mean, there may be a situation where you want to get into a very specific field where it's needed. But there are also, again, depending on what you're trying to do, what you're interested and willing to do, there are even these quote unquote postdocs in industry that you might get, like some of the big tech companies, like if you're looking to go into sort of the theoretical deep learning, they will have a specific post-grad, post-PhD role that is, under the advisement of a researcher there. And then it'll give you maybe a little bit of a hybrid, and you'll probably make 5 times as much. And if your goal is to end up, at Google anyway, great, you can go there. But I think for a lot of the other, let's say, traditional data science stuff, it won't hurt you. It's just not necessary in many cases.
And I'll ask another question from the audience, but I'll target this at Jennifer, and then others can chime in. It's what kinds of future jobs do you think there will be in data science? But I'll add the addendum, and where do you see physicists fitting in with this? Especially in this era of things like coding boot camps and such.
Yeah, I always, tell people to understand what they want, in a career in data science. I think the engineering role that ML engineer, ML ops engineer, we are only going to need more of those. The ability to design models, a good enough model for industry. A lot of that is honestly becoming commoditized, but the more models there are, the more people needed to pull the data, to maintain it, to build the tooling. I think the number of engineering roles will continue to grow, whereas some of the actual analysis, model development, I think it will grow. It will continue to grow, but just maybe less rapidly. As far as boot camps, there's they're all very different. You can, so I think some of them are pretty successful. Others, depending on, again, where you're coming from in your career, I've seen them, again, not focus maybe enough on the actual, let's say, software skills that maybe you're best off sort of trying to learn on your own. The advantage, I think, with doing a boot camp that physicists have over maybe other disciplines which, I think Jamie emphasized really well, is that ability to still problem solve and think. I think sometimes they are sort of over-focused on the tools and leave some of the thought process and problem formulation behind. But if you're getting that from your normal physics education, then, just if your goal is to become familiar with the tooling, there's, they can be useful on that front.
Anyone else?
Yeah, I would just add that, I think it's the things that I tried to point to. It's those more abstract, the mindset things that apply themselves across the spectrum of data science type tasks. So, I see these things bringing value in the early stages of building a data pipeline and validating that, in training a model and understanding how that works, an algorithm, in interpreting a model and knowing how to make it better, in monitoring the value of your model, seeing how things go wrong when you deploy your model. I think these skills are going to continue to be in demand and going to continue to be in short supply, because physics gives them to you much more directly than a boot camp ever could.
Yeah, I agree too. I just wanted to add, maybe reiterate what both of you, Jennifer and Jamie, have been saying. That it's also that I also wanted to add that it looks like the pure data science, what used to be called data science jobs, are kind of going down. There's a little less demand for them, and there's more and more demand for ML ops and machine learning engineers and things of that sort. So basically, it's like data science is transforming more into machine learning. I also, so there's certain skills for how to do this systematically, which is important. But there's also some things that, as Jamie is saying, physicists will bring to the table. How you think about what kind of tests to do, what things to look at first before you deploy a huge model, what kind of simple analyses to do first to get a feel for what would work on this data. I think those things physicists are good at, because we tend to simplify the problem.
And sort of touching on to something else that Nima had said, there's another question, which is, what kind of skills do you wish you would have developed as a student, undergrad, or grad student that would have helped you in your career? So, general question.
Yeah, for sure, coding for me.
Yeah, I was gonna say the same thing. I feel coding, I see the new kids, grad students in CS and stuff, they're so good. Even undergrads, they're great. I feel like if I had those skills back then, things would have looked differently maybe.
Right, and I think there was some mention of source control.
I would maybe, from what I've experienced, give the opposite. I think actually, there's a difference between coding quality and coding knowledge and, again, some of these practices. I think the practices around Git and stuff like that. Again, you can whip up some very complex stuff, but sometimes complex isn't as useful as reproducible. Certainly the fact that I learned to code, that my advisor sort of pushed me that way, was huge. I think it would have been hard, if not impossible, for me to have made the jump otherwise. I would say the other thing I'm really grateful for is the work that I did, outside of my research. A lot of the, what would be a project management, event planning, team development. A lot of that has made my, running teams, being a part of these sort of young organizations that are growing a lot easier than, if you're sort of many, unless you're at a very large company, a lot of them don't have tremendous managerial training programs. And so you'll find yourself in your first management position and go, what the heck am I doing? But having having worked with a lot of students at the university made that easier.
If I may, go ahead.
Sorry, you can go ahead, Nima.
I just wanted to say a small thing. I think what Jennifer's saying is very important too. I also saw a paper recently that was showing that networking and social skills are becoming more important than technical skills now in the job market, and we need to work on that. I also just wanted to add that internships was something I didn't know about really. in undergrads or grad school until very late. But that's something that's very common in computer science. It helps you build your network. It helps you learn a lot of new skills. And I feel we should encourage physics students to also do more internships in, industry in the during the summertime at least.
That's good to hear. Tony?
Sorry, I just wanted to add that, yeah, like the besides the technical coding skills, soft skills like communication, presentation, and also documentation, I think it is very important. Clear, clean documentation. I mean, I don't want to, like, maybe I would go so far as to say that code without comment is bad code. like please, like, take the time to be, clear, because it's worth it. You come back next week, you don't know what you did, or like, you have to think through the logic of what you did. It's going to be way more difficult for someone else to decipher what you did. To be nice to people and take the effort to thoughtfully document the code and communicate things, whether it's through presentations or emails or white papers, what have you. Also, I think right now, like MLOps was mentioned. I think possibly AI interpretability, understanding model biases, being more careful, thoughtful of that stuff is going to be increasingly important too. Yeah, that's it. Thank you.
Yep. So let's see, we're drawing towards the top of the hour, so maybe I'll go with some short questions. What programming language should one be familiar with if they want to have a career in ML? Tell me it's not Fortran.
I guess Python, everybody would say.
Yeah.
The more technical you are, Python. I mean, some places use R, but if you know Python, you can easily pick up R.
Yeah. I mean, there's now Rust and C++ are getting better, but still Python completely dominates the field. So.
Okay, so I'll ask a nostalgia question. So there's one that says, what do you like least about being a data science in industry? And are there things that you miss about academia?
I guess for me, it's too early to say, if I want to say, because I've been just in the industry for 6 months. But actually, I should say I like it this way, because you have more peers at the same level to collaborate with than you would get in an academic job. I actually felt kind of alone for not being able to have similar people at the same level that we could discuss every day and so on. So actually, right now, I feel it's working better, like in an industry lab. So.
Tony,
I certainly
like
miss all of the out of, I loved teaching. I loved working with the students. I, particularly enjoyed all of that. I think it was mentioned earlier, the ability to just sort of, have sort of the ability to explore something deeply and think about it. Depending on, again, the type of role you're in, you're moving so fast that you'd like to say, I want to spend just, a couple of days just really, really thinking about it. If I just had that week to sit there and think about it, I could, really make this, step change improvement. But often you got to sort of build incrementally, to the speed of it. And so I think sometimes, that's, Jamie touched on this a lot, like you see the opportunity, and as opposed to being like pushed towards the opportunity, a lot of times you have to say, not now, maybe we'll get back there. And that can be disheartening.
One thing I find very fun about data science industry is being able to very readily apply what you learn to your job. You can learn something, one day and apply it the same day, try it out the same day, see what happens, which I find very exciting. That kind of drives me to keep learning more and trying more things. so that I find very fun, and also just how I personally like to learn about different areas of machine learning as well, and see how they overlap in some ways, how they can intersect. You can learn about graph machine learning and how to regularize image classification system with a graph-like network, right? So it's really cool to learn all these things and be able to apply them. So I think there's a lot of a breadth of what you can learn and just conceive and then apply it. The thing I do miss about academia is you get to think about cool abstract things like black holes, like there's no like industry, I guess, application about black holes, but I do miss black hole physics sometimes, and being able to think deeply about things that are so exotic. And sometimes the academic environment is being surrounded by very intellectual people talking about weird things. But yeah, that's me. Thanks.
I would say for me, it's the same thing. It's the stability of the academic environment and the instability of the environment and industry. Like data science is a very competitive market. There's a lot of turnover, especially with COVID and all the uncertainty and whatnot. So just the understanding that anyone could disappear, could say today I'm gone 2 weeks from now. It's a lot harder to build team cohesion and build long-term relationships with that, where your thesis advisor, like you're not going to be changing thesis advisors every 6 months because they left the university. Like that happens, but it's rare. So that stability really affords like longer term relationships, commitments versus industry. You can keep in touch with people that leave your company, but there's a lot of turnover.
Okay. And with that, I think we're coming up at the top of the half hour. And so I just want to say thanks again to our panelists for taking time out of their work days to, share a bit of their wisdom and thoughts with us, and hopefully everyone found this useful. Sign up for our newsletter, join our Slack, and because you registered for the webinar, you will be told information about how to view the recording and all of that. So thanks again to all the audience who stuck with us till the end. So with that, I think we can stop recording and see you everyone. See you next time.
Thanks everyone.
Thank you for having us.